Welcome to a video on determining the absolute extrema of a function of two variables. Here are the steps we'll take to determine the absolute extrema. Number one, we'll locate the critical points and the function values at these points. Remember, the critical points occur where the first order partials are both equal to 0 or where they do not exist. Next, we're going to determine the max and min function values on the boundary of the specified region. Then the greatest value from step 1 and 2 will be the absolute maximum. Then the least function value will be the absolute minimum. Let's take a look at an example. Here we want to determine the absolute extrema of this given function on the region where the absolute value of x is less than or equal to 1 and the absolute value of y is less than or equal to 2. Let's first talk about the region that we're considering. This means that x is between positive 1 and negative 1,
and y is between -2 and +2.
so we're only considering the surface defined by f of xy on this region here, bounded by this rectangle. So when we talk about the boundary, there are two vertical boundaries and two horizontal boundaries. This boundary here would be x equals 1, and the boundary to the left would be x equals -1. The boundary on top would be y equals 2. The boundary on the bottom would be y equals -2. So we have to consider the function values along these four lines as well as the corner points. And here we see the graph of the surface on the defined region. And again, the highest point would represent the absolute max. The lowest point would be the absolute minimum. Let's go ahead and work through this example. So the first step is to find the critical points. So we'll set the first order partials equal to 0 and then solve as a system of equations. So the first order partial with respect to x would be y plus 0. So we want to know when this is 0 and also when the partial with respect to y would also be 0. So this would be x plus 2y equals 0. So we can tell from this first equation that y has to be 0, and if y has to be 0, then x has to be 0. So there's only one critical point, which tells us we'll have to determine the function value when x is 0 and y is 0. And that's pretty easy to do. When x is 0 and y is 0, the function would also equal 0. Okay, so this is step 1, and now step 2 is going to take quite a bit more work. We need to determine the function values along the boundary of this region. Well, as I said before, we do have to consider the corner points. Those are going to be pretty easy to do, so let's go ahead and list those. This is the point 1, 2. This is the point 1, -2. This is the point -1, -2. This is the point -1, 2. So we'd have to consider the function values for these points. Let's go ahead and do that now. So when x is 1 and y is 2, we're going to have 1 times 2 plus 2 squared. It's going to give us 6. When x is 1 and y is -2, we'll have -2 plus 4. That's going to be 2. And when x is 1 and y is 2, we'll also have 2. And when x is -1 and y is -2, we'll also have 6. So now we have 5 function values, but we still have to consider the function values along each side of the rectangle. So let's start by considering this side here where x is equal to +1. Well, if x is equal to +1, we can rewrite this function in terms of one variable. So instead of writing f of xy, I'm just going to write z is equal to, again, if x is 1, we just have y plus y squared. So now we have a function defined in terms of one variable, so we can use our calculus techniques to determine the max or min of z by finding the first derivative and setting it equal to 0. So the derivative of z with respect to y would be 1 plus 2y. So if we set this equal to 0 and solve, we're going to have y equals -1/2. So this tells us we need to consider the function value when x is 1 and y is equal to -1/2. Before we do that, let's go ahead and consider the path x equals -1, which would be along this path. Again, if x is equal to -1, we can rewrite this function in terms of one variable. we would have z equals negative y plus y squared. And we can maximize or minimize this by finding the derivative of this and set it equal to 0. So we have negative 1 plus 2y equals 0. So now we'll add 1 divided by 2. We have y equals positive 1/2. So now we need to consider the function value when x is negative 1 and y is positive 1/2. Okay, so let's find these function values. So when x is 1 and y is negative 1/2, we'd have 1 times negative 1/2 plus negative 1/2 squared. This is going to give us negative 1/2 plus 1/4. It's going to be negative 1/4. And then over here we have x equals negative 1, y equals 1/2. And the result is going to be the same. It's going to be negative 1/4. And now we have two more paths to consider. Let's consider it along this side here where y equals 2 and here where y equals negative 2. So again, when y is equal to 2, we can rewrite this function in terms of one variable. We'll have z equals 2x plus 4. When we find the derivative of this and set it equal to 0, we're going to have 2, which actually never does equal 0, which means there's no points to consider along the path y equals 2 other than the two endpoints that we already discussed. And now we'll consider along the path y equals negative 2. So we'd have z equals negative 2x plus 4. And again, if we find the derivative here, we're going to get a constant, which will never equal 0, which again tells us there's no points to consider along the path y equals negative 2 other than the two endpoints. So to finish this up, in order to find the absolute maximum and absolute minimum, we need to consider several function values. We need to consider the function values 0, 6, 2, 2, 6, as well as negative 1/4 and negative 1/4. Let's go ahead and copy all of these onto the last slide. Okay, so here are all the function values that we're considering. This function value is from the critical point 0, 0. The next four values were from the corner points of the rectangle, and these last two were from the paths of x equals 1 and x equals negative 1. And so the largest value that we see here would be our absolute maximum. So our absolute maximum is going to be equal to 6, and it occurs at 1, 2, as well as negative 1, negative 2. And the absolute minimum is equal to negative 1/4, and that also occurs in two places, at 1, negative 1/2, and negative 1, positive 1/2. Let's go and take a look at this in 3 dimensions. So here's our surface. If you rotate it this way, you can see that these two corner points here and here represent the absolute maximums on this region. And if we angle this correctly and look at the bottom, it almost looks like this is straight, but in fact it does curve a little bit. Remember, this point here was 0, 0, 0, but this point here and this point here had a function value of negative 1/4. So these two ends dip down a little bit to give us the absolute minimum on the specified region. That's going to have to do it for this video. I hope you found this example helpful. Thank you for watching.